Hi. No, it's a great pleasure and at the same time honor to greet David in his great days. I recall very well a day about 50 years ago when Arnold handed me David's paper, a copy of David's paper, David and Marsden, group of diffeomorphism and the motion of incompressible fluid. He asked me to translate it for Mathematica. Mathematica was a collection of recent translations of recent works. It was not an easy task. It took me about half a year to understand what is written in this paper, because many things which were used there were unfamiliar to me, so I had to look them up in different sources and books and papers. And after half a year, I started understanding it and managed to translate this paper, rather long, and even added some appendix to it where I explained some analytical details which were just sketched in the paper itself. It had one unintended consequence that this work and all these topics became popular in Moscow, and I was invited in different seminars to tell it. People wanted to know what it is all about. So for some time I changed the audience and told about these great things. No, as I say, it was about 50 years ago. Since that time, in fact, this paper determined the topics of my own work for all the following years following after it. So for me it was personally quite important. And today I wanted to tell about some development of these ideas, recent development in works of myself, joined with my student Alex Danielsky. He, in fact, concrete result here belong mostly to him. There was another story about the fluid, which could start about in mid-20s, but in fact started in mid-90s. Yes, it was the analyticity of particle trajectories. So what it is about? Consider M is the domain where the fluid is moving. No, it can be the whole space. Or torus, or domain in Rn with analytical boundary and so on. So it should be analytical manifold, or analytical manifold with boundary. And suppose we have solution of the Euler equations u of xt, solution of Euler equations, and consider the trajectory of fluid particles dx dt equals u of xt. And the strange theorem, strange result is that if u xt, say in hs, as has some minimal regularity, then x of t is analytic. Analytic as a function of t. Very strange result. It was discovered in different way by different people, so I can write Serfati. It was in early 90s. Then it was Frisch and Zhelegovsky. No, it was myself. Then I can remember works of Kappeler and Topalov, Inchy. Then the work of Nadirashvili, and maybe some other people whom I don't know or maybe don't remember. I think that it is quite, now it looks quite natural. So there exist, I am aware of about 4 ways how to establish this result. The first thing is the following idea. Consider the original proof of existence and uniqueness of solution of the Euler equations, which was done by Leon Lichtenstein and Nikolai Günther, separately. So consider the following to be concrete. Suppose that m equals r n. Let me r2, it's enough. M equals R2. And then we have the following. Suppose that we have the Lagrangian description of this motion. So position of the fluid is defined by position of all its particles. So if you fix initial position of each particle, then any other position differs from this by some volume preserving diffeomorphism. Yeah. So Xi m to m, volume preserving diffeomorphism. Trajectory xt, xi of t, fluid flow. Now, sorry. Velocity field u of xt equals xi dot of t xi minus 1 of t. Yeah, it is the velocity field, and it turns out that curl u equals omega of xt is omega of xt equals omega of xi minus 1 of xt t. 0 equals omega 0 dot xi minus 1 of t. Yeah, so this is the conservation of vorticity, and then the velocity, if so, the motion equation is the following: d xi dt equals, you have to take the vorticity times t, omega 0 xi minus 1, and it is vorticity at times t. We take of this vorticity corresponding velocity field, curl minus 1 of this, and all this at the point xi. Yes, so this is the first order equation of motion of the fluid. So it's equation of evolution of xi. Now let us consider the the manifold of the space of all xi. Xi belongs to say d equals s div of m. Now, if d is, we can specify the regularity of d to which functional class they belong. Let me not do it here. And d is infinite dimensional manifold, and it turns out that this vector field, so we can write d xi dt equals what, right hand side, say f of xi. Yeah. What did Lichtenstein and Günther? They proved that this function f of xi is this vector field on the on this infinite dimensional manifold satisfies the Lipschitz condition. It is enough to have uniqueness and local existence of solution. So f, satisfy the Lipschitz condition. It requires great work in studying these operations, curl and inverse curl, on one hand. But it turns out that it is not only Lipschitz, but in fact F is analytic. Is analytic vector field if you introduce here analytic structure in D, and analytic vector field in D. It is analytic vector field, and using the now standard theorem of existence, uniqueness, analytic dependence on initial condition, and so on, for analytic vector field on analytic Banach manifold. We get that solution is analytic as a diffeomorphism depending on time, and so trajectory of every point is also analytic. So, but why is it analytic? Here we have a more or less explicit formula. Here we have this formula, how to prove that something is analytic. Some function, say, is analytic. Analytic means two different things. First, this function is a sum of convergent Taylor series. Yes, so we have to write down formal vector series and then prove its convergence. It is one approach. Other approach that this function can be directly continued in the complex domain. Yeah. So here we can use both approaches. In the words of Serfati and Frisch and others, they used this approach using some commutator estimates. First they write the formal series and then prove that this series is convergent, in some neighborhood of zero. So it is one approach. Other approach is the following. Consider the complexification of D equal the set of Xi which work from M to complexification of M. What is complex? No, complexification of the whole real space is complex space. Complexification of torus, it is torus plus I times another space, Euclidean space. Yes, like this. So everything which can be complexified can be complexified. Yes, and then you note that you can continue this operator using the same formulas. Yeah. Here one thing is here this inverse to curl. So here we have to use the complex inverse function theorem, or this story has still other turn. Usually it appears that the topic of stationary flows of ideal incompressible fluid is dull and nothing interesting. So it is more or less, no, I consider exclusively two-dimensional stationary flows. It deals with solution of the equation Laplacian u equals f Laplacian psi, f of psi. Yes, psi is a stream function, where f is some function of finite regularity. And by the theorem, no, say, of Nadirashvili, we know that the stream lines are analytic. And what can be said about the structure of the set of all stationary flows? It turns out that if you consider, say, psi in h, say, s plus 1, no, why plus 1? Because hs is reserved for velocity, so psi is 1 unit more regular. And consider the set of such solutions of such equation with different f. Let me denote it by omega, for example. Omega is the set of stationary flows. In this case, what can be said about the structure of the set of omega? The first question, is it a manifold? Yes, is this some set in the Banach space, but is it a manifold? And said discovery says that it is not a manifold, no, at least it is not a smooth manifold. Yes, and it is quite disappointing, so we cannot have even good local description of this set. What can be done in this case? It is even before other questions. For example, we can ask, does it have one or many components? Yes, or does it have some singularities, and so on. These questions are still far away for us. I don't know, but even locally, it is presents something non-smooth, maybe something transcendentally complicated. And so, one of the attempts to improve this situation was done by Schwerak and Schofrud about 10 years ago. They considered the following situation. They considered the case then f in C infinity and correspondingly psi in C infinity. C infinity is regarded as a Frechet space, and in that case they managed to prove that omega is smooth manifold, and the elements of omega, the steady flows, are well parameterized, I think, by this function f. at least locally. So we can take, say, the small flows nearby some well-known flow, and then these flows are parameterized by f. In between, while they were proving it, I have already mentioned that here one of main tools is the implicit function theorem. But in Fréchet spaces, we have, instead of the usual Banach implicit function theorem, we have something like Nash, Moser, Hamilton implicit function theorem, which is much more tricky. And in fact, to prove that omega is smooth manifold parameterized by, well parameterized, at least locally, they used this theorem, and so their work was technically difficult, with a lot of estimates and so on. Why? What happened here? What was the nature of the difficulties? The nature of the difficulties, in my regard, is that they did not use the appropriate structure in this manifold, omega, namely, we have to use the fact that, constructively, the fact that the flow lines are analytic. This means that we have to consider a function as a collection of its level lines, a function in the plane. Yes, not as a collection of values of function at different points, as it is usually done, but collection of its level lines. And I asked my student Alex Danielsky to do it in the following situation, in the following setup. Consider, for example, our domain is a periodic strip, something like this. So this is X, this is Y, and this is our domain, and the L is one period. In this domain, we consider stationary flows. Yeah, these are its flow lines, or trajectories of the particles, or the flow lines for the steady flow. And the flow lines have psi equals constant. Yeah. So we can know if the domain is close to parallel strip, then and the flow lines are close to horizontal straight lines, then you can write equation of this line as y equals, say, a of x and psi. Yeah. Here psi between 0 and 1. Psi is parameter here, and for any psi we have some curve. And now we have to somehow quantify the notion of analytic curve, a real analytic curve. So we have to introduce corresponding functional space. And I define the functional space as follows. X S sigma equals the set of functions, say, u of x, such that u can be analytically continuous analytical function on x and can be continued in the strip u is analytic or holomorphic for x plus it, such that module t less or equal than sigma. Yeah, so it is minus sigma sigma. And the function is analytic in this strip, and it behaves well on the boundary. So u of x plus or minus I sigma in hs of t. I consider the function defined, periodic function defined on a circle, so t is this circle. So u of x plus I sigma or u of x minus I sigma is in this space, and the norm u in x s sigma equals a square norm u of x plus I sigma hs square plus norm u of x minus I sigma hs square. So, so we have this space, and now we assume that our domain is bounded by the curves, say y equals f of x and y equals g of x. Yes, so our domain M f of x less than y less than g of x, and f and g in x s sigma. No, s large enough, I think more than one. Sigma is some positive constant. Now, what about this function in between? We assume, so as I said, that we regard this function as collection, as a family of function of level lines. Yes. So we, instead of the function psi, we consider here the function y equals a of x psi. Yes, and now we consider the function a for any psi, any fixed psi, y of x psi in x s sigma. Yes, and and A of x plus minus I sigma psi, so it's a function of x and psi, no, say plus I sigma psi, and A of x minus I sigma psi as a function of x and psi are in HS. So this is our function space. And now if you write equation yes, now function f of psi, f of psi, f also in HS. Yes? So if you write down the equation for the function A, which is a consequence of the previous equation, where it is, one moment. The function A, we have the equation Laplacian psi equals f of psi. Now in the for the function A, which is the function of x and psi, we have the following equation: minus A xx divided by A psi plus 2 ax psi divided by A psi square minus A x square plus 1 divided by A psi cube equals f of A, f of psi. F of psi. Yeah. So here psi is one of coordinates, so it is a function, known function. Yeah, so this is a nonlinear elliptic equation, and now using the implicit function theorem, first of all, the left-hand side, yes, let us it is equal phi of A. Yeah, and so our equation becomes the following: it's nonlinear operator phi of A equals f of psi of x psi. The following operator equation, and then we can this right-hand side, left-hand side f of I is analytic operator. phi analytic operator. No, from y s plus 1 sigma to y s minus 1 sigma. And this operator, here we can use the implicit function theorem, use the analytic implicit function theorem, and have that for here we have, it depends only also on parameters, the shape of the channel, the function f small and g small, the boundary curves. So we have the following result. There exists epsilon such that if f in x as sigma less than epsilon, norm g minus 1 in x as sigma less than epsilon, norm f in h as minus 1 less than epsilon, then there exists unique solution A in x s plus 1 sigma. Analytically depending on f, g, and f. Yeah. So after we chose the appropriate, say, structure in our problem, using the fact of analyticity of flow lines, we have good and in fact very simple, reasonably simple solution and reasonably simple, good parameterization and good structure. So yes, in this, if you use this way of description of our functions, natural way, then our set omega of steady flows is positively analytic manifold. No, we got its local description, at least near the situation when our channel is parallel and the initial velocity is constant. So this is one situation. It was done by Danielski in his previous work, and now what can be the next? Steady flow can have more complicated structure, it can have critical or fixed points where velocity is 0. So the next is to study the flow with critical points. So consider the flow with one elliptic fixed point. No, it is a simply connected domain in the plane and the flow with a closed flow line like this. Here, let me briefly tell about results here. We can all these flow lines are again analytic. So we have to somehow introduce description of this function which uses these flow lines as constructive elements. Now assume that it is all close, the domain is close to the circle and the flow lines also are close to the concentric circles. So consider this fixed point and introduce the polar coordinates here. Yes, and then our flow lines has the equation R equals A of psi theta. So this is angle theta, and the flow line is psi is constant. Yes, this function, and we study the flows which are close to solid rotation. So this means that A of psi theta close to psi to the power 1/2. No, R psi is like R square. So again, R is like square root of psi. Now here, one moment. We have again the problem our problem is Laplacian psi equals f of psi. Psi on the boundary gamma equals 1. Psi at this point O, origin, equals 0. And for psi we have the following equation. So we write R equal A of psi theta. So I satisfy the following equation. Minus 1 over A psi cube 1 plus A theta square A square A psi psi plus 2A theta A square A psi square A psi theta minus 1 over A square A psi A theta theta plus 1 over A psi equals f of psi. Or simply psi of A equals of psi theta equals f of psi. So the left hand side is this operator psi. So here we have a new complication that this equation is degenerate at psi equals 0. So we have to be more attentive, and the spaces are a little bit different. So space K M gamma equals U of psi theta, such that psi P minus Q d P P minus gamma psi d Q Q over theta U in L2 for P plus Q less or equal than M. It is called Kondratiev space. It was introduced just for problems with degeneracy like this. No, and correspondingly normal, this space is the sum of L2 norms of these functions. And usual our space x m sigma equals U of theta, such that these functions are analytic, continue, they can continue to this strip between imaginary part theta minus E sigma to theta plus E sigma, U of theta plus or minus I sigma in HM. And the result here is the following. So our problem is theta of A of psi theta equals f of A, or f of psi, A1 theta equals given function, say, rho of theta, A of 0 theta is 0. And the theorem is that there exists epsilon such that if norm f minus f0 k m minus 2 gamma minus 1/2 less than epsilon, where f0 of psi equals 4. And norm rho minus rho 0 in x sigma m minus 1/2 less than epsilon. Here rho 0 is 1. Then the following is true. There exist analytical manifold Z Z in K gamma minus 1/2 m minus 2 times x sigma m minus 1/2 in the space of this data of codimension 3 such that for any f rho in Z there exists unique solution solution A of psi theta and also f rho analytically depending on f rho in Z. Yeah, so why codimension 3? It is simply explained like this. If you just solve the equation for psi, in the usual sense, so Laplacian psi is given function of psi, then and f is close to constant 4, and domain is close to unit circle, then the following can happen. The critical point, it exists, unique, but it can be not at the center of the circle. So it can be at others. So we have two conditions that this critical point is at the center of the circle. And the third condition is that if the boundary condition is that on the boundary of this domain psi is 1, and at the center it is 0 at the fixed point. And if you solve again this elliptic equation, Laplacian psi is f of psi, then we can have the fixed point, but the value of psi can be different from 0. So it is the third condition that the value of psi should be 0 at this point. And it turns out that in our representation using the level flow lines, these three conditions define analytic submanifold. And so we have as good as possible parameterization of our domain of our manifold of steady flows in the disk, in the domain which is close to the disk, by this data with this additional condition. No, we can go somehow around it in a different way. Say we can introduce additional degrees of freedom. No, it is all about more or less the same. So I fear I have no time left, so I want again to congratulate David with his birthday and wish him many further years of work. And I hope to see him soon in the future. Thank you for your attention. Bye.